Welcome back. So this is kind of the last lecture, last topic I should say, that we'll be talking about in a technical fashion. We'll end the course with a very generic discussion of other topics, but this is the kind of last topic that we'll discuss, and after that we'll solve a bunch of problems and things like that, right? So the outline of the lecture is going to be something like this. Basically, we'll introduce the problem, followed by showing how to include disturbance rejection and performance considerations, which means optimality. And then of course, what if we have both uncertain system along with disturbance rejection? This is all analysis for the time being, and then basically we will eventually briefly see how one can address the control problem, right? And we have seen many aspects of these things, and so it doesn't really require so much of new stuff that we've been doing, right? So but I want to step back and discuss a little bit about this problem of what we call as disturbance rejection here, but in reality it's even as fundamental as stability. In fact, we will think of it as actually a stability notion, and let's think about this carefully, right? Suppose if I have a system G, right? In this course we pretty much restricted ourselves to systems where we have especially if we had inputs and outputs. Basically it may look something like this. I'm using different notation, but you understand. Okay, so we assume that the G has a model, that underlying model in terms of a differential equation, and the differential equation in terms of this thing called state, and of course you have kind of an external input. In many cases that could be control, and some kind of measurable output or a performance output. The difference is basically whether we want to minimize it or is just simply set of measurements, right? In controls, basically we distinguish the measurable output and then a performance output. Performance output is which is the one that we want to kind of somehow control it, whereas measurable output is something that we have handle over, which can be used to estimate rest of the state and things like that. So anyway, but if we didn't have this kind of model, right, what can we say? Well, I mean, this model is for our understanding, and basically if we didn't have anything, we just have to live with this kind of approach, right? So in which case basically I know that Z is equal to some operator on W, and this operator could be defined through a differential equation or maybe something else. Okay, of course the only thing that we are worried about is whether this is a discrete problem or a continuous problem from a time perspective, and then accordingly deal with that. So if you actually think about it, one possible wish that we could have for a system like this is basically if W is, I'm going to write it in quotes, bounded, what can we say about Z, right? That's a generic question that we could ask. So if you want an example to hang on with, basically think about something like you're going in a car, and then basically you are trying to see the vibration effect on you, on the passenger, going on a rough road, right? Irrespective of whether we have a model to explain it or not, that's the fundamental problem, right? So what do we expect? Of course, the disturbance coming onto the road profile, the bad profile, let's say, coming onto the car does not affect as much in terms of how it is going to, the passenger is going to experience in terms of vibration and things like that. So that vibration suppression is a realistic problem whether we have an ordinary differential equation model or not. So in that sense, basically this is as fundamental as possible, and then this brings us to the concept of bounded input, bounded output stability, right? Then of course there are multiple ways of defining this, right? Even in the classical control, in fact, that's how they started. And then basically, in fact, the bounded output, bounded input stability is basically, in the classical case, if you have a transfer function, right? Let's say Z, the G of S is bibo stable if and only if poles of G of S are in the open left half plane, right? So this is classical result, right? So this is nice to know. And then in fact, what is interesting is basically G of S has a state space model, and depending on the order of the denominator of this transfer function, we get the order of that A matrix X dot equals AX plus BU, and A is Hurwitz, which is what we've been using, if and only if this is bibo stable, right? So this is excellent. That's why we could ignore the difference between the state space model and this bibo stability and things like that. Now, unfortunately, nonlinear systems are not that simple, and then basically, but then some kind of relation is certainly true. I mean, one can actually show that if the state space system happens to be stable, then it's somehow bounded input, bounded output stable. Not quite, but that's what we are trying to achieve, right? So what do we mean by bounded input, bounded output stability, specifically from the notion of bounded input, bounded output, right? So for the time being, we are dealing with continuous functions. Let's say for simplicity, we could actually assume W is a scalar. You can imagine how to generalize that, right? One simple way of let's say determining the size of this particular thing, so that we can talk about the boundedness of that, is basically define some norm over it, right? There is a very strict notion of norm in mathematics, and then we can restrict ourselves to that. So one standard thing that people use is the so-called L2 norm, right? So it's basically take the square integral from 0 to infinity and then take the power of. Obviously, only those functions that have finite number for this particular quantity is what we call as systems, signals with that thing bounded. So, in finite dimensional case, that is, simple vectors, no matter what kind of norm you define, if it is bounded in one norm, and it's going to be bounded in the other norm, and this is so-called equivalency result between equivalency relationship between various norms. Unfortunately, that's not the case in these infinite dimensional cases, that is signals or functions and things like that. What are the other possibilities of norm? Well, of course, this people typically associate with as energy. Square is typically as half mv square kind of a thing. Basically, we think of this as a some kind of energy and then take square root of that. But in reality, many times we may actually want to discuss the case where we have as simple as this, right? So just take the maximum value of W, absolute value of W, over all the time that is possible, right? So we could call this as bounded input, bounded output, and like I said, nobody says that this is better than the other one and things like that. Different applications perhaps demand one or the other. Mathematically, one is easier to deal with and the other one is more difficult, and in fact this is more practical, right? This is tractable, okay? And of course, one can actually define all kinds of norms. Suppose if you had something like one norm, then that's defined as 0 to infinity, simply this, right? Integral of absolute value. And you can define somewhere in between with some p between 0 and 1 and infinity, and we can define that, and even more general, right? So that's how one can define what we mean by bounded. If the input is bounded, can we define the output to be bounded? And then sometimes we actually may wish to have the output also be defined with respect to different norms, right? So in other words, the bypass stability could be, suppose, L2 bounded, but L infinity bounded as the output. Okay, so if I perturb the system with all L2 bounded signals, can I ensure that the output is L infinity bounded? That's the problem that we are thinking, and then that may not be that impractical. Actually, this is a fairly good problem. So in all these things, basically, we can actually now, in the case of linear systems at least, okay, basically we could define a norm on G, right, the system itself, as something like basically take all, let's say in this particular case, all L2 bounded signals, and then see the effect of that, which happens to be Z, right, and then take the infinity norm of that, right, normalize with the L2 norm. Okay, yeah. So and then basically this kind of gives us the amplification factor of this particular system, right? This is a good way of measuring the goodness of this particular system. So and then this is called induced norm. Okay, induced norm. And so for example, I'm not going to get into too many details, but if we had this W to be white noise, okay, and W and Z to, and then so we can associate some kind of white noise disturbance, and then look at some kind of output norm, and then basically the so-called H2 norm comes into picture. It's actually a norm on the linear system and things like that. But interestingly, basically the one that we will consider in the problem of disturbance rejection is basically what we call as H infinity norm, which is actually the induced norm where both input and output are considered to be L2 norms. Okay, so that's not the most practical problem, but that's the most tractable problem. Actually, in the literature, basically people define this something called as L1 norm, and it's L1 norm in a very special case. In fact, it's kind of very difficult to capture the induced norm. It's the what people want to capture is basically the induced norm between two bounded input, and capture the output also the norm in terms of this L infinity norm, the maximum value of absolute value over time, right? So you perturb the system with something that is bounded in just at the amplitude, and then see how much amplitude, and then that's kind of the ideal thing that we want to apply when it comes to vibration isolation and stuff like that, right? And then that in the literature people call it as L1 norm, and in the linear case there are some good results over there, not perfect. I mean the actual minimization problem becomes quite difficult unless it's a single input single output system. And in the case of nonlinear system, it gets even worse, right? So in that sense, basically, the question, I'm going to leave that as it is for the timing. We'll continue to assume this kind of model for our systems, right? Do we need a state space model? So to define stability essentially, right? And of course, when I put state space, I'm putting in quotes because, suppose if somebody says, oh, it's a transfer function, it's not state space, but for every transfer function, we have a state space equivalent. So I don't mean that kind of this thing. So do we actually need some kind of internal model, that came through a transfer function or otherwise to define the notion of stability? After all, here we define the notion of stability as bounded input, bounded output, right? It's a different thing. So, for every system that has state space, this thing you can easily go back and define bounded input. In fact, that's what we are going to do now. So the general question therefore becomes basically, do we need the concept of state at all to do any of the control problems, right? So anyway, we'll leave that question as it is and perhaps go back and actually look at the problem that we are going to solve now, right? So we'll come back to basically the standard model that we've been considering, except basically we'll introduce some input disturbance, and then there is a measurement output which will also have this perturbation of the disturbance. And I'm going to, for the time being, assume that some kind of norm on this particular input, and basically specifically we are going to assume that W belongs to that class of signals or functions that has finite L2 norm. And the problem here is to basically, can we actually measure the sensitivity of G with respect to this input disturbance, right? And in some sense, can we verify if this induced norm that we just spoke of in the nonlinear case, in the nonlinear case, it unfortunately is not a norm in the way we define mathematical norm in abstract spaces, but anyway, we understand, this maximization problem, is it finite, right? So if it is finite, that's good. Anyway, so this norm on the Z could be anything, and this is kind of repetition of what I was just talking about. More generally, the norm could be anything. The disturbance rejection problem is verifying if the maximization problem has some upper bound gamma, and then that gamma can be actually controlled through feedback and things like that if we know how to estimate it, right? Anyway, so these are the things that I already kind of mentioned. In the linear case, the maximization problem gives the value of the induced norm of the operator mapping W to Z, right? And then that operator could be infinite dimensional, in which case you won't have a simple differential equations that we deal with. We may have something a little bit more complex than that. So in general, it could be a transfer function or a convolution operator. And if both norms are chosen to be L2 norm, then the resulting problem is called as H infinity problem. That's what I already indicated. In fact, H infinity norm on the transfer function is why it's called, right? And then we already said if both norms are chosen to be L infinity norm, the input and output norms to be L infinity, the problem is known as L1. It's the most practical problem, but unfortunately we cannot really solve, right? So here we are going to restrict ourselves to the H infinity disturbance rejection problem. And in fact, if you open up any textbook, most of the time they only talk about H infinity disturbance rejection problem, right? And how does this work? Well, it's as simple as trying to satisfy this, right? So what did we say? The ratio of the norm of output divided by the ratio of input norm is less than or equal to gamma, the maximization problem, right? So therefore for every W, will this ratio be satisfied? So that is kind of equivalent to saying, show you what I mean by that. So we want less than or equal to gamma. So that's by squaring and then taking onto both sides, basically we will get this, right? So if we dissatisfy, then basically in the linear case, that's the same thing as satisfying H infinity norm on the linear system, right? And but then as we know from dissipativity theory that we have seen, this is same thing as determining if this G is non-expansive with gain gamma, right? So that's why we can solve this particular problem through the theories we developed, right? So, it's as simple as basically saying H infinity non-problem of linear systems generalizes to non-expansivity in the nonlinear sense, right? So therefore, in that sense, we don't have to really do much. We just have to remind ourselves how one can actually guarantee this constraint that we just spoke about, right? So, I'm going to present the result and then convince you that it is indeed valid, right? So, let's define this gamma to be this interesting function that's defined in terms of some kind of storage function V. J1 is coming from your system model, H is coming from the system model, J2 is coming from system model from various places, and basically you define this gamma x. And all we have to do is V prime F, which is the standard V dot that we've been talking about, plus H transpose Hx, that's the output function, plus gamma of x is less than or equal to 0. If somehow we can convince ourselves there is a V of x that satisfies this particular condition for this particular system, then it is non-expansive. This is, should not come as a surprise at all. We have seen this kind of things before when we were discussing non-expansivity in the dissipativity lectures, right? So, but I want to show you one more way of deriving this, right?